Yeah, thank you for the invitation, and I'm very happy to tell you a little bit about this library. Yeah, so let's start with a very short overview. What is this library? It's a research-focused homomorphic encryption library, and we built it to address the gap that we saw between all the existing libraries, which are very nice and very good if you want to build applications, but not necessarily suitable to perform research. And that's basically because the design is quite closed. And so as a position to that, Fheanor has a very open modular design, which should be open for extension, open for experiments, open for modifications, and it mirrors the mathematical structure that underlies all of the HE schemes that we currently have been developed. Fheanor is written in Rust, and it builds on the Fheanor math library, which is just the library for computational number theory. It's open source. You can, like most Rust libraries, just pull it from crates.io. And we also put a paper on ePrint so far, which gives a little bit also an introduction to the library. Yeah, to start with, I want to make this modular structure mirrors the mathematical structure a little bit more concrete. And I want to do this with an example. And I don't know how deep all your knowledge about FHE is. Probably you've heard of the BFV scheme. And as an example, I'll use the homomorphic multiplication algorithm in BFV. Looks about like this. In BFV, we've got this ring, which is in many cases set x modulo x to the n plus 1 for a power of 2n. Then plaintexts are just elements in R modulo t for plaintext modulus t, and ciphertexts are tuples of elements of RQ for where q is an integer called ciphertext modulus. So this talk doesn't really go about the internals of BFV. This is just to introduce the library. And so I also won't describe BFV in detail, but just the homomorphic multiplication algorithm. And if you write a paper relating to BFV, you would usually define it in basically these 3 lines. So if we have 2 ciphertexts and we want to compute a homomorphic multiplication, we would first compute this intermediate ciphertext, which is a tuple of 3 elements. And each element is an element of the convolution of C0, C1 and C0 prime, C1 prime, scaled by T over Q. And it's important here that this product of 2 ciphertexts is not performed modulo Q, but doesn't wrap around Q, but say is performed on the lifts of C or C prime to R. Yeah, and once you have this intermediate ciphertext, you would perform what's called relinearization, which basically can be written like this using a relinearization key, which consists of RK0 and RK1. Again, the exact details are not so important. I just want to show in an example how Fheanor really mirrors the mathematical structure of these rings and these formulas, as opposed to other libraries. So to do this multiplication that doesn't wrap around Q, usually you would lift the elements not to R, but to R modulo some larger modulus, which we could say is extended Q, modulo which you can do this multiplication without wrapping around. In Zeal, if you look at the source code of the Microsoft Zeal library, which implements BFV homomorphic multiplication, then this is the code. And I hope no one of you can read it, because I don't want to go through the code. I just want to display that it's actually not that simple to do this multiplication. To a large extent, this is rooted in actually what we do, because while these formulas look quite simple, there's actually a lot behind them. To implement them efficiently, there are lots of computational tricks that you can use to make them as fast as possible. Also, that the multiplication has there's all this lifting to Q prime and then scaling down again hidden in these formulas. So there's a reason why this is a lot of code. Nevertheless, just assume you would like to modify this algorithm. Assume you have a better idea how to compute homomorphic multiplication and want to do slight changes. It's quite a daunting task to go into this code and like make the changes to adjust the algorithm. But the code is very well documented. If you go through the details, if you know the scheme, you will be able to understand this code, I think. See, there's a lot of documentation. I found it reasonable personally, but still, making any changes, implementing something similar will take a while. And Fheanor basically tries to simplify this. And indeed, in Fheanor, you could write the same code like this. It's still not trivial. After all, we're doing a non-trivial, we're evaluating a non-trivial algorithm, but we're down from about 150 lines to 15 lines. And moreover, you can see that actually it's basically just implementing these formulas. So at the beginning, we have these like maps lift and scale down, which lift to the extended Q modulus and scale down again. Of course, they are again wrapped around. They're implemented somewhere else because they're complicated as well. And yeah, then we just lift each input ciphertext, which here are considered to be C0 to C00 to C11. And then we can compute these intermediate ciphertexts just by using the functions multiply and add of the ring with the extended modulus. So we really just can write these formulas in code here down. Like C0 plus C0 prime times C0 prime will just be ring dot multiply and then the two ciphertexts and so on. And also to compute the relinearization and the gadget products, well, if you look at the formulas, there's some inner product here, there's an addition, and there's this gadget decomposition function. Again, the gadget decomposition function is not done by this code, but it's somewhere wrapped behind this gadget product LHS operand double colon from element with. But yeah, you see the scaling down, which refers to the scaling by T over Q, is done here. We have the addition, we have the inner product. Yeah. So in a sense, this is simpler. Even though, of course, a lot of the logic is not done, but just done somewhere else, encapsulated behind some of these functions here, like gadget product or the lift functions. So the difference is really not that Fheanor doesn't do something or found a simpler way of doing things, but it just breaks the multiplication in multiple smaller components, while Zeal really only implements the multiplication directly, just delegating the entities and the lifting to other functions. And Fheanor has many more smaller components, like the lifting to another ring again, but also the ring arithmetic is encapsulated, the gadget products are encapsulated, the gadget decomposition is. So yeah, what's the difference? Which one is better? If you want to go into the details of the scheme, if you want to implement your own scheme or want to change how the scheme is done, actually you will profit a lot from the Fheanor approach. Because all these little components, like the ring arithmetic or the gadget products, they're not just relevant for BFV multiplication. They're common techniques used all over FHE. So if you want to implement TFHE or whatever, you will also need them. So it's very nice if they're available as like their own component. On the other hand, if you just want to use BFV, like the standard textbook BFV, you don't care about how the homomorphic multiplication is implemented. And in this case, this difference is really void. So if you just want to use standard BFV, then Zeal is perfect. It will provide all the functionality that you need, and it will probably be simpler to use than Fheanor. However, if you're like in the researcher use case, if you want to have your own ideas, want to experiment, want to benchmark them, then hacking these ideas into Zeal to run them will be a pain. And I've talked to many FHE researchers who basically all had the same problem. And that was the primary motivation to build this new library. And also, like, while I made this example with Zeal, I could have made it with other libraries like HELib, Latigo, or OpenFHE as well. They all follow a design that targets application builders who use the textbook variant of a scheme to build privacy-preserving applications. None of them targets an FHE researcher. So yeah, there's nothing special about Zeal here. Or just the reason why I chose Zeal for this example is that I know it best and that I find it actually the code base quite readable. Yeah. So really the main difference is Fheanor has a different audience, and that's why it's designed differently. Let's have a closer look at the design. This is an overview of the architecture of Fheanor. Each box represents, in a sense, a component, a module, and each arrow presents a sensor dependency. But this is not very formalized. This is just like an intuitive view. And as you can see, it goes from low-level operations to high-level operations. On the base, there are operations to compute entities and so on, which are absolutely vital to have an efficient implementation of FHE, really any FHE scheme. Building on that, we have modules encapsulating arithmetic in different rings. And then we have these gadget products and RNS conversions, which are necessary to perform certain not strictly arithmetic operations in FHE. And based on these, we have schemes. We have currently Fheanor contains implementations of these three schemes, of BGV, of BFV, and of CLPX. And then based on top of that, again, we have more advanced operations, which primarily is bootstrapping. But for BGV, there's also the question of automatic modular switching, of noise estimation, and so on. And on the right-hand side, there's also something that's quite new for Fheanor. There's because Fheanor contains an explicit modeling of arithmetic circuits, which is in the circuit model. Arithmetic circuits are basically the computational model you use in FHE. And well, I found it useful because it allows creating circuits that are scheme agnostic, and then you can evaluate them with any scheme. So again, it's a decoupling of the scheme itself and the way how you compute certain arithmetic or non-arithmetic operations. And of course, this is used by bootstrapping because in bootstrapping we need to compute certain functions, and it's very relevant how these are encoded into a circuit. Any questions so far? Okay, so at the beginning I thought I could go through all these modules in detail and explain a little bit more what they can do, but I think this would give a very long talk. So instead, I just want to give some examples again, some more motivating examples of different use cases and show how you would use Fheanor in such a case. So say, I don't know, you're a low-level implementation person or a hardware person, and you have this new way of computing an entity. And you want to see how much this will speed up homomorphic encryption schemes, homomorphic operations. You could do it with any previous HE library by going to the source code and replacing the implementation of the entity. But in Fheanor, you don't have to. Because of this modular design, it really allows you to just implement your own entity and then instantiate the whole library with your own entity. So actually, what you're doing is you replace this box on the bottom, and the whole library will continue to work, now using your entity. Another case. Assume you're a researcher on FHE and you designed your own very cool FHE scheme. If your FHE scheme follows roughly same techniques or ideas like any of the previous schemes in the literature, then you will be able to quite easily build the scheme using, again, the toolkit that Fheanor provides. that Fheanor also uses to implement things like BFE, BGE, and so on. And this mainly consists of the gadget products, of the RNS conversions, and of the arithmetic in all kinds of rings that are implemented. Of course, if your scheme works completely different from anything previously, Fheanor also won't help you. But that's not a common case, as far as I can say. Another case, assume you work on bootstrapping for BFE or BGE, or really anything that uses digit extraction. In that case, you might come up with new digit extraction polynomials or new digit extraction circuits, which actually a lot of people have. Like, I guess even Robin and Jai have made a nice paper on digit extraction polynomials, and there's also been like other papers. So this is actually an interesting topic of research, and every time someone comes up with a better way of doing this, the question is, how fast will this make bootstrapping? And instead of like implementing bootstrapping from scratch or hacking your new digit extraction polynomials into a library with Fheanor, you could just like plug them in. Just instantiate the existing bootstrapping procedure with your new polynomials and test them. And a final example, assume you're working on BGE and experimenting with noise estimation. Apparently that's also a very active topic of research, because for BGE, actually knowing how much noise a ciphertext has at the moment is very important to efficiently do evaluations and to not lose too much noise budget. So you might have implemented better formulas to estimate noise. And again, Fheanor will allow you to just like plug them in, instantiate the modulus management module or strategies of Fheanor with your own estimator, and it will immediately use them and then also be used by the bootstrapping procedures and so on, and cause less noise at every point. So this is like the great side. This is what we designed Fheanor to be. You should always only implement the part that you're doing research on. And all the framework, all the things that where you just follow state of the art should already be present and usable. Of course, this comes also like in a sense with a downside. And this is basically simplicity. So when you write software, you very often encounter like a point where you have a trade-off between making your function very configurable to support all kinds of parameters, of settings, of contexts in which you might use it, or to make it simple, to make default choices for all of these parameters so that a user who calls your function doesn't have to think about how to set the parameters. And in many libraries, or the other libraries basically usually, not always, but often opt for simplicity, while Fheanor usually goes for configurability. This means that if we want to effectively write a program using Fheanor, in particular if you want to go into schemes, modify them and so on, you have to understand how the schemes work. You have to know what certain concepts in homomorphic encryption are. You have to know what a gadget product is, what an entity is, and so on. You also need some mathematical knowledge, because the way Fheanor is built to mirror this mathematical structure, it readily like uses concepts like cyclotomic rings to encapsulate certain logic. So if you don't know what a cyclotomic ring is, you probably have to learn about that before you can use Fheanor. But then again, since the target are researchers like you will probably, if you're working on FHE, know all of these things already, because they're like the cookbook, the basics. But of course, this means that generally using Fheanor might be a little bit more complicated than any other library. But on the other hand, Fheanor does, while revealing mathematical detail, while revealing details of the scheme in question, it doesn't reveal, it tries not to reveal implementation detail. And this means that once you go into the internals, you need to you of course need to work with the internals of the scheme anyway, but in Fheanor at least the implementation detail is hidden, while if you hack something into the source code of other libraries, the implementation detail you'll also have to meddle with the implementation details of that library. So in this case, Fheanor is, I think, simpler to use than any other library. And so I really think it's a very valuable tool for research. Of course, I myself find it very natural to work with it, but I've also heard from already a few people here that to some extent it achieves these goals and makes it easy to build new things, or at least easier. Of course, there's always a significant amount of work involved. Okay, to already come to the end of the talk a little bit, I want to give not just an overview what were the design goals of Fheanor, but actually what's implemented at the moment and where do you want to go. I've given here an overview of different FHE libraries. I didn't include TFHE because TFHE in a sense is like a disjoint set of features. While you could implement TFHE currently also isn't implemented in Fheanor, you could implement it quite easily using the toolkit provided, but it's likely that to get a implementation that's comparable to state-of-the-art in terms of performance, you'd probably also have to implement some other ways of doing arithmetic in the rings and so on that's optimized for parameters that are commonly used in TFHE. Because, yeah, the schemes like BGV, BFE, CLPAX, GBFE, or CKKS use very different sets of parameters than TFHE does. So the design of Fheanor generally supports TFHE as well, but just because that's not my area of research, I didn't do so much implementation work in that direction. Similar is for CKKS. I think it should be easier to implement in Fheanor, but it's not not too familiar with CKKS, so I didn't implement it so far. Since we put the paper on ePrint, I already got lots of emails of people asking me to implement CKKS. I usually try to reply with, yeah, I will if I find time. Otherwise, you're very welcome to do it yourself. I will happy to accept such a contribution. So if anyone and not just for CKKS, generally, if anyone has a feature that they want to see in the library, you can ask me. If I find time, I'm happy to implement it, but it'd really be great if someone else. If you implement it, I'm very happy to merge it and include it. So other things that Fheanor has that other libraries don't have, well, bootstrapping. HElib supports bootstrapping for BGV and BFV. Fheanor supports it. I think apart from that, other libraries don't really do. Actually, HElib only implements BGV and only has bootstrapping for BGV, not for BFV. But Fheanor does both. And other libraries, as far as I know, don't do bootstrapping. OpenFHE has it planned, but yeah, unless my info is outdated, it's not yet properly available. And also, there's this column on general cyclotomics, with which I mean whether the library just supports power of 2 cyclotomics, which are the easiest, in many cases fastest case, but they're also limited in a sense in choice of parameters, or all cyclotomic rings. And currently only HElib, LOL, and Fheanor support all cyclotomic rings. And also, since it's until Robin's work, not a very big topic, the CLPX and GBFE scheme wasn't a big topic until recently, and so it also is not yet implemented in any library except Fheanor. Yeah, and I think I already mentioned the explicit modeling of arithmetic circuits, which is actually at first glance doesn't have much to do with FHE, except that it's the computational model, but it actually makes implementing many functionality in FHE much easier to have really explicitly be able to work with circuits. And the other thing is Fheanor also implements single RNS-based arithmetic as an alternative to double RNS-based arithmetic. So usually all these libraries use double RNS-based arithmetic, and FHE implements both. Again, abstracted away as two different implementations of the same ring. One doing ring arithmetic using double RNS representation, and one doing ring arithmetic using single RNS representation. And by this modular design of FHE, you can basically just choose which one you want to use and plug it in, and the library will work with that. Also, in the future, we will hopefully get bootstrapping for GBFE and CLPX. That's like one of the reasons why I'm here for this week. Yeah, and I guess there are many things on the roadmap, also still some optimizations that I want to implement. Also, the performance of FHE is already quite comparable with previous libraries, but there's still like the few last % to go. Yeah, I think that's it. The talk was shorter than expected. You're very welcome to, I invite you all to have a closer look at the library. I try my best to maintain docs at the docs.rs page. Also, they also contain like code examples and like a little bit guides into the library. And of course, if you have any questions beyond that, I'm very happy to answer that. I'm very happy about anyone who's interested in the library, who considers to use it. And finally, as I already said, contributions are very welcome. Thank you.